In this video, we are going to be taking a look at the different forms of proof that we can use to prove an implication or an if-then statement. The type of statement we'll be focusing on in this video is called an implication or an if-then statement. We write P implies Q, but in English we read if P, then Q naturally follows. Now, P is what we call the hypothesis of the implication. This is the condition that needs to be met, the if part. And the Q is what we call the consequent or the result if the condition P is satisfied. One of the examples that we use very often to show an implication, like P implies Q, is this one. If I work really hard, then the result will be that I get good grades. We are going to set up a truth table for implication P implies Q because in this, a lot of information about the different proofs is encapsulated. Now, I'm assuming by now everyone knows how to do a truth table, so I'm going to keep this quick. We will have 4 rows because we have 2 statements. We are going to alternate Q between true, false, and P we are doubling up and we are saying true, true, false, false. This means in every single row there's a different combination of true and false for both P and Q. In the first row we have that ideal condition. You do work hard and you do get good grades, meaning the implication was true. That chain of events that was promised that would follow if you worked hard was satisfied. Everything was set into motion and it worked. In the second row, you do work hard. P is true, but Q is false. You don't get good grades. This is where your lecturer was lying to you. You did your part, but the result that was promised did not follow. So in this case, we say that the implication is going to be false. This is the only time when the implication is false. We can test it. We can say the result that was promised was not delivered, even though I did work hard. I did do my part. The statement P was true, but Q is not true. In the third and in the fourth rows, we don't work hard, meaning there's no way to test if the implication is false or not. Here we will say it is vacuously true or true by default because we cannot prove otherwise. The first 2 forms of proofs that we will be doing are the simplest. We only focus on one of the parts of the implication at a time, only on P or only on Q. The first one that we will be looking at is called a trivial proof. And this is where we only have to show that Q, the consequent, is true. We will get good grades. It doesn't matter what P is. P could be true or P could be false. It plays absolutely no role in our proof. I want to show you in the truth table what would happen if Q is true. So this would be, our focus would be in the first row. And Q is also true in the third row. Can you see that the implication, the middle column for every one of these will be true, regardless whether P is true or false? In the first row, we get good grades, and we really did work hard. In the third row, we get good grades, but we didn't work hard. Maybe we were lucky. But the implication, which is what we are trying to prove, is true, regardless of what P does. Our second form of proof is vacuous. Now, this is where we only show that P is false, meaning our focus in the truth table is going to be here, again, at the third row and the fourth row. This is where P, the hypothesis, or the trigger that sets in motion a bunch of events, is not true. The trigger isn't being pulled, so we cannot even test the implication. But most importantly, we cannot prove the implication is false. So you will see in both of these cases, the implication is vacuously true. It doesn't matter what Q is. We don't work hard. So whether or not we get good grades has no effect. The whole thing falls flat. The switch isn't even pulled. The trigger isn't pulled. The switch isn't flipped. The trigger isn't pulled. So in both cases, if we start with a false hypothesis, or if we can show the hypothesis is false, the whole implication is going to be true by default. In both of these cases, we ignore the other part of the implication. For trivial, we only focus on Q being true. For vacuous, we only focus on P being false. We completely ignore what Q is. The first two forms of proofs were grouped together because we only focused on one statement at a time, P or Q, and we completely ignored the other one. For the next three forms of proofs, we are going to be focusing on both of the statements involved at the same time. So we are also grouping them together to see how they relate to each other and how they differ. The first form of proof is called a direct proof, and this is where we assume that P, the hypothesis, is true. We did work hard, and we show that Q will naturally follow from that. We will get good grades. It's called a direct proof because we follow the direction of the implication arrow exactly. P points to Q. If we work hard, then we will get good grades. The next form of proof is called a proof by contrapositive, sometimes referred to as an indirect proof. This is where we change up the direction, but we still prove the exact same equivalent. We assume that Q is false. We don't study or we don't get good grades. And we want to show that if the implication is still true, it means that we didn't study hard, we didn't work hard to begin with. A proof by contradiction is very similar to a proof by contrapositive, and this is why it confuses a lot of students when they first try and compare these two proofs. It also involves us assuming that we didn't get good grades. So it assumes that the consequent is false, not Q is going to be true. But at the same time, it assumes to the contrary that P is also true. It assumes that we did work hard and at the same time we didn't get good grades. The difference between these two, the contrapositive and the contradiction, both of them assume that we didn't get good grades. Both of them assume that the result that was promised was not delivered on. The main difference is in the contrapositive, we show that, well, we didn't actually do our part. So the implication is still true. It's just that the condition wasn't met. And that's why we didn't get the results that were promised. In the contradiction proof, we assume that we didn't get good grades, but we assume to the contrary that the implication itself is false. We did study hard or we did work hard, but we didn't get the good grades. And we show that this results in a big issue. This results in a problem, a contradiction, which means our assumption to begin with was wrong. I want to show you just before we get to an actual example of these in action. I want you to focus on the direct proof. This is where we assume P is true and we show that Q naturally follows. This forms the first row of our truth table. Both P and Q are true, meaning the implication is going to be true. For the contrapositive, focus on we are assuming not Q. So it could be either the second row or the fourth row. But we are assuming that Q is false, and we are showing that P must then also be false. So in the truth table, we are actually here in the fourth row, and you can see in the fourth row, our implication is true. For the contradiction, we are looking at the other case, where Q is going to be false, but we assume that P is true. Can you see where the problem comes in? Our assumption is that we are in the second row, meaning our implication is false. We are trying to prove the implication is true. So we are making a wrong assumption. we are trying to show that this results in a massive contradiction, meaning it must have been one of the other cases. The implication must actually be true. So just to summarize in this table before we move on, our first row in the table is going to be where we use a direct proof, or it could be one of the cases where we have a trivial result because Q is true. So the first row, we have these two forms of proofs that we can use. The second row, we have our proof by contradiction. So here, don't have a lot of space, but this is where we have the contradiction. We have the P, which is our condition being met, but we don't get Q. So the whole thing is false. In our third and fourth rows, just to summarize, this is where we have vacuous truth. So this is where a vacuous proof would be beneficial. But in the fourth row itself, this is also the row where we use or where we focus on the contrapositive, where we assume Q is false and we show that P is going to be true. Let's prove the same statement using three different proofs: a direct proof, a proof by contrapositive, and a proof using contradiction. What we are trying to prove is an implication. So again, we have an if-then statement. If n is odd, let's call this P of n, then 7n minus 5 must be even. Let's call this Q of n. What we are trying to prove is P implies Q. Let's look at the different forms of proof. Our first one is direct, and this is where we follow the direction of the implication, as simple as that. We are going to assume that n is odd, so n is equal to 2k plus 1, where k is some integer. And we are going to try and prove that 7n minus 5 must then naturally follow to be even. So what we are going to do here is then we are going to expand a little bit on 7n minus 5. Now if we replace our n, we get 7 times 2k plus 1 minus 5. And let's multiply out the brackets. This gives us 14k plus 7 minus 5 is plus 2. What do we want to show? We want to show that this expression is even, while there is a common factor of 2 that we can remove, and what's left has to be an integer. But what is going to be left? We will get 7k plus 1, and that is indeed 7k plus 1. This is an integer. So 7n minus 5 is even, exactly what we wanted to show. And our proof is done. What did we do in the direct proof? Just again to summarize, we assumed P and we showed or we proved that Q is going to naturally follow from that. For proof by contrapositive, the next one, what do we need to show? Well, instead of showing P implies Q, we are going to show that not Q implies P. So not Q of n must mean that P of n is also going to be false. So here, what are we going to assume? Well, we are going to assume for some integer n that 7n minus 5 is not even, but odd. So let's say 7n minus 5 is equal to 2k plus 1, where k is an integer. What do we want to show? We want to show that if this is the case, n has to be an even number. Otherwise, we get a big problem. So what we can do over here is we can say, well, this is logically equivalent to, if we manipulate the equation slightly, keep the 7n on one side, but take the minus 5 over, we get 7n is equal to 2k plus 6. What I see a lot of students at this stage do, it's not incorrect, it's just not very convincing. They will take this equation and they will try to solve it for n by dividing by 7 on both sides. So they will give this, n is equal to 2k plus 6 over 7. Mathematically, there's absolutely nothing wrong with doing this, but what they will then do is try to say this. Remember, we are trying to prove that n is even. So we are trying to prove that we can write it as a product where 2 is one of the factors and the other factor is an integer. If we factorize out a 2, we get in brackets k plus 3 over 7. And then a lot of students will, because this is simply what they need to write to finish their proof, they will say, well, k plus 3 over 7 is an integer, and we are done. This is an even number. K plus 3 over 7 is not always an integer. There are values for k that we can substitute, like 4, which will give us an integer, but there are a lot of other values that we can substitute for k that don't result in an integer. So this argument from this point to deduce that n is even is not convincing, and it does not hold any water. So we are not going to follow this approach. I'm going to delete this piece of the proof, and we are going to try something else. Not too different, but just a little bit more convincing. What I'm going to do over here is I'm going to take the 7n and write it as n plus 6n. This is still equal to 7n, and this is still equal to 2k plus 6. What I can do now is I can take this one of the n's and solve the equation for that one. What we end up with on the right-hand side is 2k plus 6 minus 6n, or we can rewrite this as 2 times k plus 3 minus 3n, where this bracket is definitely k plus 3 minus 3n will definitely always be an integer. So this means n is even, and this is exactly what we wanted to show. So using the contrapositive, which is equivalent to the original P implies Q, we have shown that the result is true. The last one that we are going to do is a proof by contradiction. I'm changing my color to red because we are going to start with a wrong assumption. For the contradiction proof, we are going to assume the following. We are going to assume that the hypothesis is true. So we are assuming n is indeed odd. Let's say some 2k plus 1, where k is an integer. But, and let's just be very clear, we are assuming to the contrary that 7n minus 5 is not even as promised. 7n minus 5 is actually odd. Let's say 2l plus 1, where l is an integer. We are going to try and use these two facts to construct a big problem or a big contradiction. We know we've already proven that the original implication P implies Q is true. So if we are assuming P implies Q is false, it has to lead to a contradiction. So for the third type of proof here, we are quite safe to know that we will be able to find a contradiction. The question is just how and what is the contradiction. So I'm going to try and keep this simple because we do not have a lot of space left. What I'm going to do is focus on my 7n minus 5. Over here, part of our assumption is that we assumed 7n minus 5 is odd. So keep this in the back of your mind while we are busy. Right, what are we going to do? We are going to expand on 7n minus 5. Very similarly to what we did in the first proof. We are going to take our n, which we've assumed to be odd, and we are going to plug it in. Now 7n will be equal to 7. Our n is 2k plus 1 minus 5. And then we get 14k plus 7 minus 5 is plus 2. And this we already did in proof number 1. We can write this as 2 times 7k plus 1, where 7k plus 1 is an integer, meaning 7n minus 5 is even. So in our assumption, we assumed 7n minus 5 is odd. It's equal to some 2l plus 1. And in the same breath, we've shown here that expanding 7n minus 5 gives us that it is an even number. This is our big contradiction. We cannot have that a number is both even and odd at the same time. So this means the assumption that we made, P as well as not Q, was a false assumption. It was a wrong assumption. And this means the original statement was actually true. Just to compare again the different forms of proof that we used here. For the direct, we assumed P of n and we showed Q of n. For the contrapositive, what did we do? Well, here we assumed not Q and we showed not P. For the contradiction, we assumed, let me just put it here to the far left, we assumed P and not Q. Can you see how these two, the contrapositive and the contradiction, are very close? Both of them assume that not Q is true. The one, we show that it has to follow that not P is true. But in the contradiction, we assume immediately P is true. And this results in a big problem.